Hello everyone. Good morning. So we are starting the second session by Jan, who is presenting the massively parallel computation of upper and lower bound. And here he talks about the AMPC as well, and some remaining proof from the previous time, and continue for the rest. And we should finish by this model, which is the second model of handling big data today, and we will continue the rest of the class next week. Good. So yeah, I think you can.
Okay. So thanks, Mohammed. Yes. So on Tuesday we talked about a massively parallel computation model, and for short recap, so the massively parallel computation model is a parallel model when a computation happens in rounds. We have many machines, usually denoted by M, and the machines are capable of to store only S bits of data. However, they can perform arbitrary polynomial computation in rounds. And between rounds, they can exchange the data in an arbitrary way with the only condition that no more than S bits can be sent or received by any machine. And this was the model for upper bounds. And for lower bounds, we introduced a shuffle model, which captures the same, which captures exactly the behavior of the MPC, but it's a little bit more formal and therefore easier to prove lower bounds. So in the shuffle model, instead of machines, we have gates. Each gate has the input of each gate can be at most S bits, and then again we in the shuffle gates were assigned to rounds. However, and this was for the purpose of the simulating the rounds in the MPC model, and it worked in such manner that a gate could receive only bits from these gates that were assigned a smaller number of rounds to the gate itself. Yes, and then okay, and then we gave some theorem that stated that any MPC algorithm can be simulated in S shuffle within the same number of rounds, and the number of gates that is needed for this simulation is the number of rounds of the MPC algorithms times the number of machines using the MPC algorithm. What does not change is that if the MPC algorithm use S bits per machine, then the size of the input to each gate is also S. So this was the reminder from the previous lecture, and today we'll be looking at specific properties of functions that are computable by the S shuffle model. Okay, so to start with, we'll be looking at polynomials, and basically, if we have this shuffle model, we assume there is some n bits of input, and for simplicity, we can assume that the shuffle model outputs one bit, either 0 or 1. So we can think about the whole computation as a function from the set of 0, 1 to the power of n to either 0 or 1. And then possibly it could be arbitrary function, but what we will prove today is that actually all functions that can be represented as in the S-shuffle model are polynomials of a limited degree. And this will be helpful for us for the lower bounds, because many problems have been considered as polynomials, and many results have proved what is the maximum possible what is the minimum degree for a polynomial to be to correspond with some problem. And then so just a quick recap about polynomials. Okay, here's a mistake. We'll be talking about polynomials not over reals but over 0, 1. So is gonna be a little simpler. Over 0, 1. And then, right, if you have a function, the polynomial is, if you have a function of, say, n variables, then the polynomial is very, yeah, it's an arbitrary composition of addition and multiplication of these variables. Then if you would like to, so yeah, so polynomials over 0 and 1 can represent like different logical function. If you would like to think about the end function, so a function that outputs 1, where if and only if all initial bits are 1, you can think about this polynomial. And then if you want to think about OR function, it could be represented as this polynomial. So this is an example that polynomials are, at least for some functions, well suited and can be used. Of course, not every function even over 0 and 1 can be represented as, I mean, every function can be represented as polynomial, but the degree of this polynomial can be arbitrarily large. So there is like always this trade-off between how big the degree of the polynomial could be. So what we would like to prove is that if our S-shuffle model takes R rounds, then the size of the so the size of the input to gates is S, then the polynomial that it computes can be of degree at most S to the power of R. So this will be our result. Yeah, and then if on the other hand, if we knew some lower bounds for some problems on the degree of the polynomial that represents this problem, then we could have lower bounds for these problems. Okay, so. Okay, so here is exactly the theorem that we want to prove. Yeah, as I said before, we could forget about this k here. We can think about the computation as a function from n bits to only 1 bit, and then we want to prove that this function is representable as a polynomial of limited degree, and this is basically what this theorem says. So how are we going to prove it? As usually in such cases, we will use induction. And here is the claim that we will try to prove by induction. If you have a gate, say G of V, we want to prove that there exists a polynomial, and assume that this gate is in some round R1. So we want to prove that there exists a polynomial of degree at most S to the power of R1 that agrees that somehow accepts this gate. What do I mean by accept? So we want to have a polynomial that, as is written here, we want to have a polynomial V Z that takes the initial bits to the whole computation, and it outputs 1. So this should be equal to 1 if and only if G of B is equal to that. Okay, so somehow this polynomial can recognize whether the inputs, whether the given input agrees, condition on the given input, whether in gate G, G of V is equal to Z. So this is quite easy for the base case where we have input gates. So there is, for short recall, input gates took only 1 bit, either 0 or 1, and this was like ith bit of the computation. And if you want to have, so if the ith bit is, say this is x1, xi. So if the ith bit was 0, then we can use this polynomial. So obviously inverts this bit. So yeah, whenever this bit is 0, this polynomial outputs 1. So it satisfies this property. And then for input bit 1, we can use just xi, and for everything else we can use 0. 0 it shouldn't accept. Okay, and then we have the induction step. Yeah, so we would like to we would like to consider cases. What are the what is the possible input on ith position to gate G? So we have here G of B, and so there are three cases. It could be either 0, 1, or the silent mark, this one. So for the first case, we consider that Zi is either 0 or 1, which is symmetric, and then because so there is like one critical thing that we assume that at most one process sent 0 or 1 to this gate, and so this was some process U, and then we know from the inductive assumption that the computation of this this gate can be represented as a polynomial, and because only this gate sends the valuable information to the gate V, we can use these polynomials to represent to check whether our computation whether our so if you would like to have a polynomial P of V of Z of the input bits, so all input bits, and maybe I will just add 3 in here. So we would like to have a polynomial that is able to verify whether the computation made by G agrees with Z, but only on the ith position, so only on this input position. So we could use we could use the polynomials for this gate because we know that only this gate can send a meaningful bit to the gate V. This was our assumption that no more than one we have to schedule our circuits so that no more than one gate sends a bit on this position. Although there can be like other bits on different positions. So we can then we can just take for this polynomial that's okay. So this polynomial is defined such that it's equal to 1 if and only if G of V of I equals to Z of I, Zi. So this polynomial checks whether the ith position, ith bit of these gates agrees with ith position of the given set C. And we use this using, we got this using the inductive assumption from U, and we observed that this polynomial is of degree at most s to the power of R of V minus 1, because we have this condition that whatever gate sends an information to gate V, it has to be in the previous round. Okay, and if you would like to have okay, yeah, and then that's it for ith position of gate I, and then we should figure out what we like to do if we want to have agreement on all positions. Oh, okay, yeah. First there is a second case. Okay, yeah. Maybe before diving to the final conclusion, there's also the second case when no bit has been received on the ith input, and then we can use exactly. Okay, yeah. Then we can use 1 minus the polynomials of all gates that has sent nothing to gate V. And again, because we only did a subtraction of the previous polynomials, then the degree still remains s to the power of R of V minus 1. Yeah, so what we got from the previous consideration, so we got some number of polynomials that each of them agrees on different input position of the gate V. What should we do if we want to have a polynomial that agrees on all these positions? Okay, nothing easier. We can just multiply all the polynomials that we got so far. So such that the value 1 is achieved on if and only if all these positions actually agree, which was like marked 1 for each of these small, I mean, each of this smaller polynomial, and then we have to verify what's the degree of the new polynomial. So because we assume there is only s inputs to the gate V, and we knew that each of the polynomial had degree at most s to the power of r of 3 minus 1, and we did multiplication, so we know that the degree of new polynomial is this degree times at most, times s at most, and this is exactly what we wanted. It equals to s to r of v. Okay, so this was like a brief sketch how the induction goes. Yeah, and what does it prove? Again, let me repeat. It proves that if we have a function that is computable by a shuffle circuit, then this function can be represented as a polynomial of limited degree, and the degree depends on the number of inputs that are allowed to a gate and on the number of rounds that the S-shuffle circuit use. Observe one thing, that this degree does not depend on the number of machines, of gates in total. So maybe in some rounds we could have many gates that are like parallel to each other, in the sense that they are not dependent on each other, but the degree of the polynomial would be still the same. Okay, so what can we do with? One side mark. It's not true that if we see a polynomial of degree at most s to the power of r, then this polynomial could be recognized by an S-shuffle circuit of r rounds and input size s. And here below we have an example of such polynomial. Yeah, I'm not going to draw why it couldn't be represented, but it can be verified. And then having this theorem, so actually the positive theorem, what can we do with this? Okay, so let me start by introducing monotone graph properties. Graph property is monotone if adding an edge to this graph does not change this property. So for example, connectivity is a monotone property because adding an edge to a graph doesn't change the property whether the graph oh, actually it's not, but I guess it's not because okay, sorry, I take it back. Connectivity is not monotone in this sense. Okay, can I give you an example of I don't know, probably not now. Yeah, probably not now, but I assume that. Okay, yeah, now I don't know any monotone graph properties, but anyway, there is a theorem that if you have a monotone graph property, then you can lower bound. Okay, if you have a monotone graph property, then you always can think about the input, the graph as some set of bits, and then you can think about the output as either 0 or 1, so as a decision problem. And then it can be proved that if actually the problem that you consider is this monotone, has this monotone graph property, then any polynomial that agrees with the function which we'd like to compute has to have at least okay, it has to have at least this number of okay, it has to have at least two okay, let me parse what's written here. Okay, so we know that okay, we know, okay, so we have a function that represents our problem, and we would like to we like the function to be a polynomial, and we know that the decision tree complexity of the problem is at least this. So we know that 2 to the degree of f of the polynomial f to the power of 4 is equal to n squared divided by 3 minus some element of smaller order. So from this, we can deduce that the degree of this polynomial is at least the right-hand side divided by 2 and taken to the power 1/4. So from this, we can deduce that if we have some monotone graph property, and we know that we know that yeah, and so from this we have a lower bound on the degree of a polynomial that can represent a monotone graph property. So we know that the degree of this polynomial must be at least something. On the other hand, what we just proved is that any shuffle circuit that has few rounds cannot represent polynomial that has too much degree. So we for a single problem, we have bounds from both sides. Then we can just compare these bounds, and this is how we get a lower bound on the number of rounds of a monotone graph property, for instance. And this is written in this theorem. So not so useful for now because I don't know any monotone graph properties, but it can be also proved that for an undirected connectivity, so just basically for connectivity problems, so for determining whether a graph is connected or not, whatever polynomial, whatever, if you like to have a polynomial that accepts only graphs, so outputs only one for graphs that are connected, the degree of that polynomial has to be at least n choose 2. And this actually, because like I said, connectivity is not a monotone graph property. To prove this, we have to use some other ideas, but this actually can be proven, and this gives us directly the lower bound. Let me see whether I have this lower bound on the next slide. Okay, I don't. So just yeah, just to make it have it on slides. If we have a computation with gates of the input size S, and we want to have R rounds, then we know that S shuffle circuit can so then we know that an S shuffle circuit with these parameters can represent only polynomials of degree S to the power of R. So if this S shuffle circuit accepts, I mean, if it agrees on all inputs with the polynomial that represents connectivity, we know that this this quantity has to be greater than n choose 2. Okay, and this is exactly how we get the lower bound for the number either of rounds, assuming some input size of the gates. So we can have a lower bound on the number of rounds. Basically, this implies that the number of rounds is at least a log of S of n up to some cost. Okay, and then Yeah, so this is, and because S shuffle, as we proved, is stronger than the MPC model, it also gives us the lower bound for the MPC. For instance, if the memory is so if S is exactly into epsilon, it gives us a lower bound that depends on this epsilon. Everything cancels out. If memory is smaller, say, I mean, if we allowed only log n of memory, then we have some lower bound that is like a little bit larger. But there are some absolute lower bounds that show that it couldn't. I mean, it's possible. I mean, it's not possible to solve connectivity in constant number of rounds in the MPC model. Okay, so this is about unconditional lower bounds. The next slide. Okay, yeah, one interesting thing is that at least for the S shuffle model, so in what I presented, the number of machines it doesn't matter. So in the sense that we can allow like arbitrary many machines in a single round, and they can. I mean, the complexity of the computation that this S shuffle model can perform does not change. And this can be used here to prove that actually the lower bound that I just presented is tight. So if we allow arbitrary many gates, then in this number of rounds, we can compute any polynomial in this many of rounds, we can compute any polynomial any polynomial of degree at most s to the r, where s is the input size and r is the number of rounds. And this is basically done by iterating over all possible inputs. We would like to distinguish between all these many inputs. So we can think that we have like, in our computation, we have a gate for each possible input, or like a gate that encodes each possible assignment of bits to this variable. So we will have 2 to the n gates, and then we would like to have something that from input. I mean, in the beginning, I mean, in the first round, we have n gates that take either 0 or 1, like depending on the input. And then what we like to have, we will have a complete tree that, so like a tree that starts from this vertex and from this gate, and it recognizes whether it got yes. So okay. So okay, if we know the basic idea is that if we know that the output, I mean that the gates in the last round here are 2 to the n gates for all possible inputs, then we can think that each gate could have we can think that for this gate we create 2 new gates that recognize the first half of the input and the second half, and they send only 2 bits to this gate, whether these 2 bits are 1, and this gate knows that what the input is. And then again, this gate should recognize the first half of the corresponding input, and this gate should recognize the second half of the corresponding input. And then we have the size of the pattern that we want to recognize in each round. So, and if you have this was in case we have like the size of the input 2, so we have. But if you have the size of the input s, so we can use s pieces of the. We can split the input into s pieces, and then for each of these pieces we can have a gate that recognizes whether it's follows the pattern that we want to have in the final gate. And in each step, we divide the size of the, sorry, yeah, we divide the size of the pattern that we want to recognize by S. So we need exactly log of bases of n rounds to go from input patterns of length 1, which are exactly input gates, to length patterns of to patterns of length n, which are exactly the output. And then this is how we can do this computation. Although you can observe that like somewhere in the middle here, the number of gates will be huge, because we need possibly all gates that represent different patterns of like length n over 2. So I guess it can be even n choose n over 2 gates in some middle rounds, which is obviously exponentially large. But nevertheless, it can be proven that a shuffle circuit exists, and it computes the function in a small number of rounds, and we've bounded input size of the gate. Okay. Okay, so one could ask, okay, what are the possibilities for stronger lower bounds? So what you would like to, so for instance, we can think that we would like to limit the number of machines that we have per round, sorry, number of gates that we have per round, and maybe then it will be possible to obtain a stronger lower bound or something like this. And this theorem doesn't show that it's not possible, but what it shows is that under some conditions or some properties, I mean, proving lower bounds, assuming some properties of the S-shuffle model, is as hard as proving that, or is at least that hard as proving this NC1 class is not equivalent to P class. And this, so I don't know if you already talked about NC1 and P. P is the class of the computations that we expect that are solvable in polynomial time in sequential. Yeah, in sequential model, so on non-deterministic Turing machine, while NC1, I guess, is the class that we expect, the class of problems that we expect that are solvable in log n to the power of 1. So yeah, in log n rounds in pyramid. So these are the two classes, although it's not a formal definition, but like carries on the intuition that is behind these classes. And then the conditions that okay, and then what are the conditions that make proving a lower bound in the new model as strong as this conjecture? So it's worth to mention that this conjecture is actually known for many years and it hasn't been resolved yet, and it's like very important, but also I would say rather hard to open problem in in the complexity theory. And then okay. So the properties is that if one would like to have a model that has then the number of machines or equivalent to gates is polynomial in the input size, and then here is like the usual assumption that the input is at most S of n, so like some number of bits, we can, so this is S. And then if we assume that the power of each machine is, this is actually limitation of the degree of the polynomial. So if the computation in each machine or equivalent gate can be can be as complicated as a circuit of depth log of S of n, then distinguishing between so proving that actually some problem is not solvable in this scenario will be equivalent to distinguish between these two classes. So basically it says that okay, yeah, so this is what it says. Okay, and then so there is a question, can we prove anything better? I mean, can we somehow overcome this this hardness and maybe having some other assumptions? Can we prove something better than the lower bound that we just had? That it was obviously an unconditional lower bound, but I mean, it showed only that, for instance, connectivity cannot be solved in less than 1/epsilon rounds or something like this. While our best algorithms for connectivity in the MPC model use log of n rounds. So it's like very large mismatch between these two quantities. So yes, at least no. So the answer is yes and no. For connectivity, we do not know any better lower bound, but assuming that we cannot prove any, so assuming that there is no better algorithm for connectivity, we can use this conjecture to lift many other lower bounds from different models and to get lower bounds for other problems. And this is what the conditional hardness is. And then in like next two slides, I will try to briefly discuss the concept. Okay, so as I said, the assumption is that the connectivity in the MPC requires at least log of the rounds, what is the diameter of the graph. So this is the conjecture that we make, and then condition on this conjecture, we are able to prove that some other problems do not admit fast algorithms in the MPC. And this problem are maximal matching, which is just a matching of, maximal matching is a problem of finding a matching so that no edge can be added to this matching. So this is, yeah, so the matching is maximal. It's just, it's just maximal. Then synchronous orientation is a problem of orienting edges of an undirected graph such that each vertex gets at least 4 outgoing edges. Let me double check whether it's correct definition. Oh, no, sorry, almost. So synchronous orientation is orienting edges of the regular graph such that each vertex has at least 1 outgoing edges. So we want to, so we are given an undirected graph that is the regular, so every vertex has degree B, and we want to verify whether the edges can be oriented so that, as I said, each vertex has at least 1 edge that goes to some other vertex. And this again, so conjecture on connectivity, it can be proven that this problem does not admit any faster than log of n algorithms in the MPC. And finally, delta squared vertex coloring cannot be done faster than log of log star n, or this is the Ackermann function. And here, this is just a vertex coloring, but delta squared corresponds to the degree of the graph, the maximum possible degree. So yeah, under these conjectures, we are able to get much more. So we are able to have much more knowledge about what is solvable or not. But still, this is like a local problem whether this conjecture actually holds or not. Okay, and probably in the last slide. Okay, and okay, so I guess this would be it. So thank you everyone for listening and your attention. And if you have any questions, I'm happy to answer them.